Today, I'll explain linear map, focusing on isomorphism. More precisely, it is just homomorphism of a vector space. So, homomorphism is a structure preserving map. So, the most important map in the mathematics is homomorphism because, for example, set theory, we have a map. Map is sending some matrix to some set to the other set. This is called map, and if it is set, its result is also set. So in set, we don't say much, just we don't need to distinguish much. It is just a map. But the question is, if it is a group, after map, because it is map, it can just give a set. In a group, what we want is that the map sending group to group. This is called homomorphism in a group. Similarly, we are in vector space. What we want is we are using vector space, and the resulting set is also vector space. And this is what we want today, and the map having this property is called vector space homomorphism, and another name is linear map. So linear map is, then what is linear map? Of course, you need two vector space. Let us assume both are K vector space, V plus heart, but in V, and W and plus addition and S multiplication in W. Because I want to specify the domain of the operator, I clearly write V and W and heart for specifying it again. And map phi V to W is a linear map. What we want is relating this. How we relate this plus addition and S multiplication. When it is, so we want, because addition and S multiplication is the most important basic operation in the vector space, we want to keep the result. So for all V1 and V2 in V, if map of V1 plus is on V, V2 becomes 5V1 and plus 5V2. It is on W, so plus V becomes plus W, but keeping their summation. This property is called linear, additive, sorry. The other property is called homogeneous. In mathematics, of course, not in physics. For all V in V, and for all A in K, so number K, phi of A times V is A times phi V. Of course, again, this is multiplication on W. So multiplication in V becomes multiplication in W directly. This is called homogeneous property. And if this map satisfies both these conditions, then it keeps addition, it keeps the S multiplication directly. So it is called linear. The map is called linear, or the map is a linear map. And yeah, sometimes for the homomorphism, we always write this phi W. So this is just the same notation, V to W. You can see every thing appears same, but it is above case is usually used for the homomorphism case. There are many. One thing you can always check these two to check linearity, but for checking you can use simpler. So theorem for all a, just a, maybe a, number a, and for all v1 and v2 in v, if phi a heart v1 plus v2 is a heart, of course w phi v1 and plus is also become w and phi v2. In this case, again, heart becomes heart w, I miss w v here, and plus v becomes plus w. So in this case, by choosing a equal 0, then phi v2 becomes v2, or then maybe I just say this, by choosing v2 equals 0, then it is the second case. By choosing a equals 0, you can have a equal 1, you can have a first additive condition. So this, if you check this is always true, the above two condition is always true. So you can just check this, then it is linear. I think the most simplest thing is that zero map. Let me write something like 0. It is nothing by every element becomes 0 in W. This is the simplest thing. And why not? Then how about our identity map? It is everything becomes sorry, identity map is not defined when they are different. So let us find, identity map is V2 itself. It is homomorphism into itself. Do you remember what is the name of it? It was endomorphism, if I remember correctly. Yeah. So this is identity map, which is just ID V is V2. I already write it. To specify domain, I write maybe V. It is just like everything becomes itself. And in the above, there is I send everything 0. Can you send everything with others? No. If you send everything, for example, to V, let me write Q. Let us write similarly phi equal V to W, and everything send some W is non-zero but unique W. If you send everything to W, some W, then this is not linear. It is simple. You have phi 0 plus V is phi 0 plus phi V W. But this is nothing but phi V. So phi V is phi V plus something, which becomes the same. So this should be 0 in W, and 0 in W is unique, but so you always need 0 in it. So it is not true. So this is not linear. And in fact, one of the condition you can check simply is that for linear map, phi of 0 in V should be phi of 0 in W. Other thing can be 0, but 0 should be go to 0 vector. This is one of the most important property of the linear map. And the other is that you have to know is isomorphism. I hope you remember isomorphism. Isomorphism is nothing but bijective homomorphism. So it has inverse homomorphism. And because homomorphism is linear map, it is bijective linear map. So in vector space or linear algebra, bijective linear map is called isomorphism. It is called so vector space isomorphism. And if there is some phi isomorphism, if there is some isomorphism, we call V, W, and W are isomorphic. More precisely, V plus S multiplication in V and W plus in W S multiplication in W are isomorphic. And we usually write V is isomorphic to vector space W. So this is notation for isomorphism, and this is to specify it is vector space isomorphism. I will write this. So some people usually do not write VEC, but I like to clearly writing it. So this is vector space isomorphism. So when isomorphic, if you remember, means just exactly the same. So in the language of vector space, we will not distinguish V and W. They have all the properties the same. So this is what we call isomorphism. So now, today we first learn what is linear map. Linear map is nothing but just the homomorphism in the vector space. So it sends vector space to vector space.